Hello, good people. Welcome to this episode. So, if you've been following this series, then I am sure this notebook is not new to you and you are familiar with most of the code that I have in there. So, basically, we've been focusing on learning about the multi and bandit algorithm, which helps us to take optimal decisions under uncertain conditions. And today, we're going to focus on how to use upper confidence bounds to balance between exploration and exploitation. And so I'm going to continue to use the code that we have already created in this notebook, and then we will learn more about the UCB or the upper confidence bounds algorithm. And so just to give a recap of what this notebook does, so these are the regular imports, and I use this function to plot what the agent is doing, basically to see how the cumulative rewards increase over time. And this class here is an environment I have created where you are able to bootstrap an environment with different reward probabilities and different reward values. Okay, so over here I have an example, an instance of the environment that we have used in all the different agents that we've implemented. So we have the random agent, we've implemented the epsilon greedy agent, we've implemented softmax exploration. I think I have not done a video about this. I'm going to do that. And I've also implemented Thompson sampling, which I haven't also done a video about. But this video is a special request from some of the viewers, and so I thought I should make this video to explain upper confidence bounds. Okay, so let's get started. So I am sure by now you understand that the whole idea of the multi-arm bandit algorithm is to help us to take optimal decisions under uncertain conditions. And such reinforcement learning agents are always faced with a situation where they have to keep a balance between exploration and exploitation, where exploration is taking unknown actions just so it can learn more about the environment and hopefully discover optimal actions to take. And exploitation is also taking the most optimal actions that it has learned about. And the reason it is important for it to keep a balance between exploration and exploitation is if it exploits too early, then it can miss out on the chance on actually discovering the real optimal action to be taken. And if it explores all the time, it will also miss out the chance of getting the most rewards by exploiting. So all the algorithms we have looked at are using different strategies to balance exploration and exploitation. And today we are going to look at a class of algorithms which goes by the name being like basically it says being optimistic under uncertainties. Okay, and the focus of this video is upper confidence bounds. But before I explain the upper confidence bounds, I'm going to explain to you a very simple optimistic agent which is going to prepare you to understand how the upper confidence bounds algorithm works. So this is the formula for, you can call it a policy for pulling the arms for the upper confidence bounds algorithm. This formula might look scary to you, but once we are done implementing it and with the explanation I will give you, I am very confident that you will understand what it does. So, like I said, let's start first by building a very simple optimistic agent. The whole idea of these class of algorithms known as optimism in the face of uncertainty is you start off by being optimistic. Okay, so basically the agent has a set of arms that it can pull from, and it is usually guided by its estimation of the action values, which are the Q values that we have always been calculating in the different implementations of MAB that we have. Now, with the class of algorithms known as optimism in the face of uncertainty, what you do is you make the agent optimistic. And the way you make the agent optimistic is that your initial Q values are set to high values. And because those values are high, it is going to encourage the agent to explore more. Now, through the exploration and the re-evaluation of the Q values, the agent will come to the point to realize the true action values or the Q values for each of the actions that it has been taking, and it will be reducing exploration on actions that don't yield good result, and it is going to explore more on actions that yield more result, and that is going to be the exploitation. So like I always do, I'm going to use code to explain this to you. So let's get started, and let's create our optimistic agent class. So I'm going to create a class called optimistic agent, and I'm going to make it inherit from object, and I'm going to give it an initializer or a constructor. So these are usual Python stuff, and you're going to pass in the environment. And this parameter here, initial kill, I'm going to set it to 10. I'll explain why. And then initial visits, I'm going to set that to 100, and I'll also explain why. And like we always do, we set max iterations to 2000. Okay, and so inside our constructor, what we do is self.environment is equal to the env self.initial kill is equal to initial kill, and self.initial visits is equal to initial visits, and we say self.iterations is equal to max iterations. Okay, so in case you're wondering about what these initial visits and initial kill arguments are, like I said, for all the class of algorithms in the group of algorithms that we call optimism in the face of uncertainty, and in this particular instance, the optimistic agent, what we do is we start off by giving a high estimate for the kill values, and because the kill values are high, and also because the way the arm is chosen is to take the max of the kill values, you agree with me that if we start off with kill values that are high, what we are effectively doing is we are encouraging the agent to explore more. Okay, so this initial kill value is the initial value that we set our action, the estimate of the action values to. And by this point, you understand that the action value is just the average of the rewards that the agent have accumulated by taking a particular action. So if it has taken the action 4 times and the total reward it obtained for taking those 4 actions is 20, then the kill value, which is also the average, is 20 divided by 4, which is 5. So if you look at most of these agents that we already implemented, you can see that the Q values was initialized to 0. But in this case, we are going to initialize our Q values to whatever we pass as initial Q. Okay, so let's do that. So as usual, we're going to build our act function, which is we're going to start off by saying our Q values is equal to np.ones. So usually we do np.zeros, but now we are doing np.ones, and then .k arms, where the k arms is the number of arms that are available to the agent to pull. So if you have been following these videos, now you know what this k arms is by now. Okay, so instead of setting it to zeros, we set it to np.ones, and we multiply each of them by the initial kill. Okay, so basically what I'm doing is I'm setting the kill values to a list of initial kill. So if you set initial kill to be 1000, then what you're basically telling the agent is that for all the arms that are available to you, the estimate for each of these arms is 1000, and because they all have the same estimate, the agent is going to explore most of them. Okay, but the question is, how do we make sure that the agent stops exploring actions that do not really yield good results? Think of this scenario. Let's say you've been given a population of a group of people whose average height you are supposed to estimate. Okay, one way you can do it is you can readily go ahead and then take a sample of the population. So if there are 10,000, you can take about 1,000 of them, measure their height, and then you find the average, and you can say, okay, for this population, I think based on the sampling that I did, this is their average height. But in this case, you realize that you only get their average height after you have done your sampling and you've calculated the average value. One other way you can do is you can just guess. You can just look at them without measuring anything and you make a guess. Okay, so we all know maybe how tall 2 meters is. So you can just make a guess that, okay, by looking at a few of the people from this population, I think their average height is 2 meters. Okay, you start from there. Now you realize that the more you measure their true height and you estimate the average, the more the true average converges to like its truth value. So basically, if you estimated 2 meters to be their average height, you can see that the more sampling you do, the closer you get to the true height. Okay, so what is going to happen here is, yes, we are giving it a very high initial Q value, but over the time, as the agent explores and reevaluates the Q values, it will begin to learn the actual true Q values for each of the arms, and then it will begin to explore, it will begin to exploit, guided by the arm that pays more. Okay, so what we are going to do here is, now we have our Q values set to initial Q, and then we also always keep an arm count, which counts the number of times a particular arm has been pulled. So we're going to say self.env.k arms, and then we multiply this by self.initial visit. Now, if you're wondering, why do I set initial visits to 100? So basically what I'm telling the agent is, I am assuming I have visited each arm 100 times and my estimation of their values is 10. Okay, the reason it is important to set your initial visits to a relatively big number, and by relatively big number I mean you choose your initial visit with respect to the max iterations. Okay, it is very important that you set it to a big enough number, because if you set it to, let's say, 1, after 1 visit the agent will lose the optimism aspect of it. So you set it to a bigger value, but then you have to choose it in consideration to the max iterations. I mean, I am doing a maximum iterations of 2000. So if I assume that I have done it 100 times and I know the agent still has 2000 times to actually learn the true action values, then I am confident that no matter how bad my estimate is, the agent still has the opportunity to learn the true Q values. Okay, so you set your initial visits, which is just telling the agent that you have visited each arm, or you have pulled each arm 100 times, because we have set it to default to 100. Okay, now we need our array that keeps the rewards for pulling each arm, and for that we set to zeros. And the reason we are setting this to zeros is, first, the initial kills are estimates, so they are not true, but what will help us to arrive at the true kill values is the arms rewards. And because we have not done any iteration, we start off by setting them to 0. Okay, and then we go to our usual list, one for getting the rewards and one for calculating the cumulative rewards, so that we can plot our graph. Okay, so we say for I in range self.iterations, what we're going to do here is we say arm, so the arm to pull is equal to mp.argmax kill values. So this is where you need to understand what's going on. Because the arm we pull is determined by the argmax, and the argmax simply means which Q value is the biggest. So the arm that has the biggest Q value is what we pull. So when the agent start off knowing that each arm has a Q value of 10, then each of the arms can be pulled. But in this case, it's going to be the first arm. It will pull it, and then it's going to get the actual reward for pulling that arm, which is going to affect the re-evaluation of the Q values. We write that code very soon, but the true reward is going to affect the re-evaluation of the Q values. And if the initial estimation is too high, you will see that the true reward will be forcing the actual Q values to converge to its true value, and the agent will stop pulling that arm if it is not good enough. Okay, so we pull the arm and we get the reward. So you say self.environment.choose arm, and then we are going to choose that arm. So anytime we choose an arm, it's like we've pulled that arm, and the environment is going to return the reward for pulling that arm. So now we have to do what we need to do to re-evaluate the action values, or the Q values. So we say the arm rewards for that particular arm plus is equal to reward. So basically we are reading the reward we know for that particular arm, and we are adding to what is already there. Okay, so arm rewards for that arm plus is equal to reward. These are common codes that we've written over and over. And we say arm count for that arm. So we're also updating the number of times we have pulled that arm, because we need these two values to be able to evaluate the actual Q value. So we say Q values for that particular arm is equal to the arm rewards, so which is basically the total rewards it has obtained for pulling that arm, divided by the arm count, so the number of times that arm has been pulled. So arm count arm. Okay, and what we do here is we say rewards dot append, and then we add reward, and over here we say cumulative rewards dot append, and this is where we are calculating the cumulative reward. Okay, so we say cumulative reward dot append is basically just the sum of our rewards divided by the length of the reward. So the cumulative reward is basically just the average reward that the agent is getting on each iteration. Okay, so now we come here and we return the dictionary that we need to plot our graph. So we return arms is equal to arm count, so we know how many times each arm has been pulled. We get the rewards to be the rewards list, and we also get the cumulative rewards, which is going to return the cumulative rewards. Okay, so now we have a very simple optimistic agent here, and I believe you understand it. If you don't understand it, let me know in the comments so that I can help you, because it is very important that you understand how the optimistic agent works. Now I'm going to create an instance of the optimistic agent. So optimistic agent is equal to optimistic agent, and I already have an instance of the environment that I have bootstrapped up there. So I'm going to set my initial Q to 10. I mean, we don't need to pass it because that is the default up here, but I'm just doing it for clarity's sake. And I'm going to say initial visit is equal to 100, and I'm going to say max iterations is equal to 2000. All these I don't need to supply because they are the default values, but I'm just doing it so that when we want to change it, it's going to be easy. So I'll say optimistic agent history is equal to optimistic agent dot act. So the agent is going to act for 2000 times, and what we're going to do here is we're going to print the total rewards, that is going to get total rewards, which is the sum of we're basically calculating the sum of optimistic agent history, and then we get in the rewards part of it. So rewards. Okay, so let's see what's going to happen here. So we run it, and it is returning a total of 1437, which is quite not right. Let me see the environment that have been bootstrapped up here. And so this environment, I think I ran one experiment with this environment and I forgot to rerun this cell when I bootstrapped it again. So let's come down here. Let's rerun our class. I think I have run the wrong class again. Okay, so optimistic agent, and I'm going to run this optimistic agent, and yeah, now we have 38,727. Let's see if it is able to figure out which one is the best arm. And I'm just going to copy the plot history function here. I'm going to paste it here, and I'll give it the optimistic agent history instead of the other one. So you can see that indeed our agent has been able to figure out which arm is the best arm to pull. It has figured out that it is the arm 2, and it pulled it more times than all the other arms. But you can see that it did a good work by exploring. I mean, I wouldn't call this a good work of exploration, but at least you realize that the agent didn't neglect any of the arms at all. So what it basically did was it explored all the arms, and because of the re-evaluation of the Q values, you see at this point what we are doing here is we are re-evaluating the Q values. So remember the example I gave you about the height of a given population. You start off by making a guess, but you realize that the more you measure the actual height of a sample of the population and evaluate the average, you begin to see that you are getting the true height of the population. Okay, and so it wouldn't matter what initial value we gave as a Q value, it will be replaced by the true Q value. And once the agent has learned the true Q values for each of the arms, it will begin to exploit. And the reason it will begin to exploit is how it chooses the arm. Okay, the policy for choosing the arm is basically look at the Q value that gives you the maximum value. Okay, the Q value with the maximum the arm with the maximum Q value is what becomes the arm that the agent is going to pull often. And so because we have started it off by telling that the Q value for each of the arm is 10, we are encouraging it to explore, because like, okay, whenever it's looking at the argmax, it can end up with any of the arms because they all have the Q value of 10. But after choosing the arm, it gets the reward and it re-evaluates the Q value, and regardless, it is going to find the true Q value, which is going to guide it to either explore, which is going to guide it to either explore or exploit. And the way it will exploit is it is going to keep choosing the arm with the biggest Q value. So this is the easiest way to implement an algorithm that is optimistic in the face of uncertainty. Okay, if you don't understand anything, leave it in the comments and I'm going to explain. But it is important that you understand this before you watch the upper confidence bounds video, because the upper confidence bounds video is going to build up on some of the challenges of getting this optimistic agent to work. You might be wondering, how did I come up with the initial Q value of let's say 10? The way I got to know I can choose 10 as my initial Q value is, look at this. I looked at the environment that I created and I realized that I'm 1 gives 95, I'm 2 0, I'm 3 25, I'm 4 10 5, and then 2 for the last arm. And so in my mind I'm like, okay, I realized that for arm 1 it has 0.01 chance of giving you 95, which is less probable, and it has a 99% chance of giving you 10.05. So I realized most of the rewards that the agent will be getting is 10.05, and so if I strike the average, it is going to hover around 10, and that is why I chose 10. Okay, so this simple implementation of the optimistic agent requires that you understand the environment well to be able to choose correct values for your initial Q and your initial visit as well. For the initial visit, I have explained to you that you have to choose it in consideration to the maximum iterations that you'll be performing. Let's see one problem here. So I'm going to change my initial Q to, let's say, 1000, and by chance you can see that it is succeeding. Let's change it to 10, and now you can see that it is performing poorly. The reason is that I gave it an initial kill of 10,000, and after, I mean, basically it doesn't have enough iterations to overcome the false Q value that I have given it, and so the agent will behave suboptimally. So if I run again, you can see it becomes purely probabilistic. Let's try some other different values. So let's say this is 0, 0, 1, and this is 1, and so there's some playing around for you to do to figure out what are these correct values that you need to set for initial kill and your number of visits as well. So what we're going to look at next is the upper confidence bounds, which is an upgrade on this very simple optimistic agent thing. So I want you to take a look at this formula here, and the formula basically says the arm to pull is equal to the argmax of not just the Q value. So Qn of A is basically the Q value for a particular arm, but this time you can see that it is the argmax of the Q values plus some constant times the square root of log n over kna. I'm going to explain everything to you. Now this log n here is the log of the number of times we have pulled the arm. Okay, so for example, in this loop, what will be the n here is going to be our I, because the more iterations we do, the more we pull the arms. Okay, so we just take the log of how many times we have had to pull the arm, then, and this is going to be any of the arms. It's just the number of times, or a count of how many times we have actually pulled the arm. Okay, any of the arms, and the denominator here is the count of the number of times we have pulled a particular arm. Okay, so what is happening here is our agent wants to balance exploration and exploitation, but we need a way to decide how to explore. Okay, and what the upper confidence bounds does is it is similar to what the optimistic agent does, but you can call the upper confidence bounds realistic optimism. The simple optimistic agent we have implemented here, as you saw when I played with the values, you need some level of understanding to be able to use this agent correctly, and so you have to do some tuning. So now the initial kill and the initial visits have become hyperparameters that you have to tune about your agent to be able to get it to work. Now, with the upper confidence bounds, we are using statistics to let the agent know how to explore. Okay, we are using statistics to teach the agent how to explore. And so when it comes to the upper confidence bounds, the only hyperparameter that we have to tune is the C, which is just a number. It's a number we have to choose, and it is going to be dependent on the problem that you are solving, and even the dynamics of the environment that the algorithm is being implemented for. So there's some tuning you have to do there, but at least you realize that we only have to tune C and not two hyperparameters for us to tune, because the difficulty of tuning two hyperparameters is any change you make to one has an effect on the other one, and balancing how each one of them affect the other becomes a difficult problem. So I'm going to take this formula once again, and I'm going to explain it before we write the code, and in writing the code I will explain it as well. So like I said, we have this formula here, and that is the policy with which the agent is going to pull the arm. How it does the pulling of the arm is, yes, it evaluates Q values like we have always been doing for all the agents that we have implemented. But now it is also going to include some uncertainty factor, which is a measure of how uncertain the agent is about a particular arm. Okay, and then the agent is going to pull more the arms that it is more uncertain about. Because the more it learns of an arm, the more certain it becomes of its Q value. So it is sure that for this arm, I am close to its true Q value. But for the arms that are less explored, it has to explore them more. And that is going to be guided by this term of the formula here. So we'll call this term U, that is a measure of uncertainty in our formula. Now, don't be scared by the log and the mathematics here. It is really, really simple to understand. Ignore, for the sake of understanding, ignore the first term, which is Q of A. Ignore it, and let's just focus on C times the square root of the log of n divided by Kn of A. Now, I want you to also ignore the constant because it's a constant anyway, and let's focus on the square root of the log n over Kn of A. And I've explained to you that the log n, the n in this function represent the iteration, that the current iteration, okay? And then it is divided by the number of times that we have explored a particular arm. Now, because of this logarithm for the numerator, what is actually happening is that the numerator is going to grow slowly, or it is going to grow logarithmically, okay? Yeah, it's like, think of big O notations and how they grow if a function has a big O notation of log n. You can see that such algorithms grow slowly with respect to the number of input. So because of the log here, or you can look at a log scale and you can see that it is a curve that grows slowly as n increases. Okay, now because this grows slowly as n increases, you can see that if we have not explored a particular arm enough number of times, let's say we have explored it 0, then what this term is evaluating to is some value divided by 0. And because of the 0, it is like the uncertainty term is going to be almost infinite, the uncertainty term here, because you're dividing something by 0. We will prevent division by 0, but I'm just using it as an example. So if let's say we have explored it just one time, then you realize that the uncertainty term will be bigger, because look at it, the numerator is growing slowly, but the denominator is growing anytime you pull a particular arm. So it's like dividing a small number by a number that is growing faster. And so if this number, the denominator, is bigger, you can see that the number becomes smaller. Like this term, the square root of whatever is up here, becomes smaller. And so the uncertainty for that particular arm will reduce as we pull it more and more. Okay, and so the agent will keep exploring, guided by the uncertainty, how uncertain it is about a particular arm. And when it gets to the point where it has pulled it enough that the uncertainty term is approaching 0, then it will stop exploring it, because it knows that it is very certain about it. And it will get to the point where it has explored all the arms enough that it will begin to exploit the best arm. That is the intuition I want you to have. And now let's start writing code for the UCB, or the upper confidence bounds algorithm. So I'm going to call UCB agent, okay, and I'm going to have object, and then I'm going to do init, the usual stuff that we do for all the agents, so the environment. And now we will be setting our constant. We can set it to default of 2, and we say max iterations is equal to 2000, and we say solve.env is equal to env, solve.c is equal to c, solve.iterations is equal to max iterations, and then we do our act method here. So let's build our act method, and it's the usual code that we have in all the agents. So q values is equal to mp.zeros. Mind you, we are not doing optimistic initialization as we did here. In this case, in the simple optimistic agent, we had to set Q values to some optimistic values. In the UCB, upper confidence bounds agent, we don't have to set optimistic because it is going to explore guided by how uncertain it is about a particular arm, and it is statistically driven, as you have seen in the formula up here. Okay, so we're going to create zeros self.env.k arms, and we can also come down here and we'll say arms count. So arms count is equal to np.zeros, and we're going to do self.env.k arms, and I mean, we can set data types. So d type is actually proper to do it all the time. So arms count is an integer, and the q values, you can give it a data type of np.float 32. Okay, that should be fine. And down here we're going to do arms reward, which is the total rewards for each arm. So now you should get used to this pattern. So self.env.k arms, and it also has a data type of np.float 32. Okay, now let's go ahead to create our usual rewards and cumulative rewards, which is also this. Okay, now what we're going to do is we'll say for I in range 0 self.iterations plus 1. I will explain why this is necessary. Okay, so in all the previous agents, you realize that I started iterating from 1. But in this particular agent, I'm starting iterating from 0, and that is why I am adding 1 to the number of iterations, because otherwise the range function will generate 1 less than max iterations, and so that is why I'm doing range from 0 to iterations plus 1. Now the question is, why am I starting counting from 0 instead of 1 as I have been doing for all the past agents? And the reason is, when I was explaining this formula to you, I told you that kn, or the denominator here under this term, which is c times square root of log n divided by kn of a. By the way, this term also measures the variance of the different arms. So like I said, it is giving you how uncertain the agent is about the individual arms. Okay, now the kn here represents how many times the agent has pulled a particular arm, and as you realize, our array that holds how many times the agent has pulled a particular arm is initialized to all zeros. So at the start, the agent hasn't pulled any of the arms. And so if we don't do something about it, you realize that this formula here will end up dividing by 0, because the kn of a is how many times the agent has pulled a particular arm. So at the start, it hasn't pulled any of the arms, and we would be dividing by 0. And you know that division by 0 in any programming language causes something to go kaboom, and we don't want that. Okay, it's going to cause some terrible error to happen, and we don't want that in our agent. So what we're going to do, first of all, and this is a very important thing to remember whenever you have to implement the upper confidence bounds, is you have to first of all start off by at least pulling each of the arms once. Okay, pull each of the arms once, regardless of whether it is a good arm or it is a bad arm. Pull it at least once. And the way we do that is, in the iteration, I will check if I is less than the length of q values. Okay, then I'll start off by saying arm is equal to I. So what I'm basically doing here, is, if it is the first time it is pulling, I say, okay, choose arm 0. If it is the second time, choose arm 1. Third time, arm 2, arm 3, up until we have pulled each of the arms. And the way we know how many arms we have to pull is to get the length of q values, or we can also do environment.k arms, as we have been doing over here. Okay, so what I'm saying is, for starters, for the first iterations, just make sure you pull each of the arms, okay? And then otherwise, which means after it has pulled each of the arms, this is where we calculate the uncertainty, okay? The U term that I explained to you. So I'll say the uncertainty is equal to self.c times np.sqrt np.log of I divided by the arms count. Don't be confused about what's going on here. Remember that arms count, why did I call this arms count? And for most of them I called arm count. Okay, let's change this to arm count and arm reward. I just want to be consistent. Okay, so what's happening here is I am just evaluating the inner term, this term here. It is equal to the constant, which I told you is a hyperparameter that you have to tune for your specific problem. You have to try different values that works best for your specific problem, multiplied by the log of the iteration divided by how many times a particular arm has been pulled. And this in code is this. So oftentimes you see a formula and mathematically it looks like something that is fearful, but you implement it in code and you realize that it is something that is very easy to do. Now over here, remember I am dividing by arms count, and arms count is a numpy array. So I'm doing a vectorized computation of the uncertainty for each of the arms. Okay, so I is the ith iteration, and arms count is this arm count array here. So I am basically evaluating how uncertain each of the arms are, how uncertain the agent is about each of the arms, and then see how we're going to decide on the arm to pull. So we say the arm is np.argmax, the argmax of the q values plus the uncertainty. Okay, so the whole formula that looks fearful about upper confidence bounds, this whole thing here that looks so fearful if you are not mathematically inclined, is what we have turned into code over here. So first of all, we evaluate the uncertainty term, which is c multiplied by the square root of log I divided by kn of a, and then the way we choose the arm, that is the entire formula here. So we just take argmax of the q values plus the uncertainty estimation for each of the arms. Okay, now that we have this, the whole flow becomes like every other agent. Okay, so we say reward is equal to self.env.choose arm, and then we're going to choose that arm, and then everything else follows as we already know. So I think I should be able to copy what is here, and paste them. This is not a good practice, but I'm getting tired of typing. Okay, so arm rewards plus is equal to reward, arm count plus 1. Okay, q values, we evaluate the q values again, we append the rewards, blah blah blah, cumulative rewards. Okay, I think we are safe to continue on this path, and so I'm going to return what we usually return so that our plot function can also do its work. So hopefully I haven't copied things wrongly from the other agents that we implemented, and we should be ready to try the UCB agents. So UCB agent is equal to UCB agent, and what we're going to do here is we're going to pass it the environment, and we're going to set C to, let's say, 5, and max iterations 2000. I don't need to set this once again because there are default values for them, but for the sake of clarity, that is why I am doing that. Okay, so I'll do UCB history is equal to UCB agent dot act. So we're going to make our agent act over 2000 iterations and hopefully learn what is right. And because I'm a lazy guy, I'm going to copy the print function here so we can print our total reward for that agent. So I'm going to use UCB history instead of OA history, otherwise we end up using that of the old algorithm. Aha, now I shouldn't have copied. So UCB agent has no iteration. So what is here? What is here? What is here? Iterations. Okay, now I'm paying for copying and I hope I don't have to pay more. Okay, so now you can see that our upper confidence bounds agent is also making 37,931.1, which is close to what each of the agents have been giving us. Now let's go ahead and plot the history to see how the cumulative rewards came up and how it's decided on the best arm to pull. So we plot this and you can see that it is also doing a very wonderful work by finding the optimal average reward, and you can realize that it settled on ARM2 because of course from the environment definition ARM2 is the best arm to pull. Let's verify that from here. So what is in our environment? Our environment is this, and ARM2 has 75%, 75, yeah, 0.75 probability of giving us 25. And the first arm has 0.01 probability of giving us 95. So even though the reward is good, is big, the probability is so low that the agent thinks it has to be pulling this one. Yes, because 75% of the time to give you 25, and there is some that 99% of the time is going to give you 10. So even by common sense and by inspection, you realize that you have to take this action most of the time. So if you come down here, it shouldn't be surprised that all the agents, like apart from the random agent which didn't act intelligently, you realize that all the agents settled on action 2. And so when we come down here, it is no surprise that the upper confidence bound agent also settles on action 2. But look at the difference between the upper confidence bounds agent and the simple optimistic initialization agent. You realize that the optimistic initialization agent wasted some of the time exploring on actions that were suboptimal. So it chose each of the actions quite a good number of times, and then it finally settled on action 2. But if you come to the upper confidence bounds agent, you realize that it didn't waste a lot of time on most of the actions that do not pay out well, and it's focused on action 2 and explored a few more times on action 3, because by definition of the environment, action 3 also rewards quite well, because action 3 is where you can get 10.05 99% of the time. So once again, the focus of this video was to show you how to implement upper confidence bounds guided by this arm selection policy here. But for the sake of understanding, I started off by helping you to implement a simple optimistic initialization agent that works by assuming that there is no evil in this world. It starts off by being naive and instead of pulling the arms until it realizes the arms that are of true values, and then it settles on them. And now we came down here and we have implemented the upper confidence bounds agent, which is guided by this formula here. Basically, you evaluate your Q values and then you do some uncertainty measure for each of the arms, and you explore more on the arms that you are less sure of. And once the agent has learned the true Q values, it settles on the right value, and so we ended up doing the correct work. So thank you very much for watching. Don't forget to subscribe, and I'll see you in the next video.